The next topic deals with dissolving stuff. Now, we talked about dissolving, but we never really did explain how that works. And then once you've dissolved something, how do you measure the relationship between what's been dissolved and what is doing the dissolving? And it changes for a lot of what we call solutions. A solution, as we talked about way back when in chapter 1, is a homogeneous mixture where you can't see the stuff in it. Salt water is a good example of a homogeneous mixture that we call a solution. So let's talk about this. So let's suppose that we are going to dissolve sodium chloride in water. Well, here's the deal about sodium chloride. Sodium chloride is made up of positive ions, which are really small because they've lost their outer level of electrons, so they shrink dramatically. The negative ions are really large, and so we get this kind of we call a conjugated system or alternating system of positive and negative charges, and it keeps going in three-dimensional directions. This way, and out in front of the board, behind the board. Okay? And so, let me do one more row here so you can get a really good idea of what is happening here. Okay, now, let's focus on this negative ion. Now, if this is sodium chloride, you know that sodium is the positive ion. And remember, sodium has one electron that's outermost level, but when it becomes an ion, it loses that outermost level, so it shrinks dramatically. And that's why they're so small. The chlorine grabs that electron from the sodium and becomes really large because the pull of the protons in the nucleus is not nearly as good as if it had equal amounts of protons and electrons. So the electrons are pulling away, plus they don't like each other, and so they're repelled from each other, so they get really big. So there's no such thing as a molecule of sodium chloride. It is simply part of a large crystal lattice complex. Okay? So water comes along. Now water is what we call a polar molecule. Now when we did the Lewis dot structure, we did everything in 90 degrees, but we also said in actuality that this bond angle was somewhere around like 104.5 degrees or whatever it was, 109.5 degrees. And so it's obtuse, and so it creates what we call a split of the charges. So in other words, this side here is positive, and this is a lowercase delta. Means kind of positive, not a true positive charge. But the electrons in the single bonds with the oxygen here go in that direction. We use this symbol to show that the direction of the electrons is towards the oxygen, because the oxygen is electronegative. And what that means is when the oxygen and hydrogen make a deal to share an electron, the oxygen is kind of laughing to himself or herself, whatever, because he or she has no intention of sharing equally. It wants to pull all the electrons for that, so that makes that side there kind of negative. So we call this a polar molecule. Okay, so if you put a chunk of salt in water, there's now going to be contact made between the water and the salt crystals. And so what we will see happening here is that the positive side of the water is going to get attracted to the negative oxygen. Or that's chlorine here, sorry. So we're going to see it bonding like that. Now, I want you to notice this right here has 6 sodiums bonded to it. 1, 2, 3, 4, 1 in front, 1 behind. Every negative ion has 6 positive particles. Likewise, if you take a look at this positive particle of sodium, this has 1, 2, 3, 4, 5 in front, 6 behind, 6 as well. So the formula of NaCl is actually Na6Cl6, but we reduce it down by dividing both by 6 and we get NaCl. But technically it's Na6Cl6. But what happens here is that a collision occurs. The water hits that, collide to that, and the collision is strong enough to break this bond and pull it away. So we get the chloride negative with the water bonded to it. And we call this Cl. I hate you so much. Whatever. Call this Cl negative aqueous. Okay? Years from now, this thing will no longer be a thing. Alright, so now the negative side of the water right here is going to be attracted to this positive particle right here, and so when they collide, and they collide such that the oxygen hits that sodium, then you get this going on here. And that collision is hard enough to break the bonds between that sodium and that those two chlorines there. And then this comes free to become tiny iota sodium with the oxygen attached to it, the hydrogen's tagging behind, because this is the negative side of water, that's the positive particle, and it's not to fit. And we call this Na positive aqueous. The aqueous refers to the water molecule attachment. Now, in actuality, just like the salt crystals, you actually find 6 waters bonded to it. So you actually have another water right here, another water right here, another water right here, and then one in front and one behind. So you get 6 waters on that thing, and the same thing happens over here. We got H, O, H here, H, O, H here, and H, O, H here. And then one in front and one in back. So you actually have 6 waters for every ion that has been attacked and pulled apart. So the bottom line is this. In order for dissolving to occur, it has to have collisions. No collisions, no reaction. Okay? You want a chemical reaction, the two have to collide, and they have to collide at such a spot that it's going to break the bonds that that substance has with other parts of the substance or compound. Okay? So we got to have collisions. And it's really a 3-step process. One, solute to solute bonds must break. Now, when I say solute, what I mean by solute is that this is the stuff being dissolved. Okay? Second step, at the same time when this collision occurs, you have to have solvent to solvent bonds break. And solvent is the stuff that's doing the dissolving. Now, how do we know which is which? Well, the biggest difference is whatever you have more of will be the solvent, whatever you have less of will be the solute. Example of that would be like vodka. Vodka is 40% alcohol, so that means 60% of it is water. So that means then the alcohol that is the vodka is just ethanol, and it's going to be the solute and the water is a solvent. Now, when 60% alcohol, which they call 120 proof, and there are blends out there like that, then that means 60% of the alcohol is actually dissolving the 40% of water. So it's a matter of perspective. It's all about quantities. Okay? All right, so that, and then the third step is that new solute to solvent bonds are created. And that is when we use the aqueous phase, if the solvent is water. Which most of the time is. Not all the time, but most of the time it is.